to one and all present here. I, Dinesh Kumar S. from the Department of Mechanical Engineering, on behalf of East Point College of Engineering and Technology, welcome you all for the National Conference on Recent Advancements in Mechanical Engineering and Materials. I would like to request Dr. Harishanand, HOD, Department of Mechanical Engineering, to welcome the gathering.
Good morning, one and all.
Good morning, sir.
I'm really delighted to be standing here in front of you. I have the honor of inviting and welcome you all for today's inaugural of National Conference on Recent Advances in Mechanical Engineering and Materials, RMM 2020. Sharda Shardam Bhoja Vadana Vadanambuje Sarvada Sarvada Smakham Sannidim Kuru Ya Kundendu Tusharahara Davala Ya Shubra Vastranvita Ya Brahmarchuta Shankara Prabhutivihi Sada Pujita Devai Sada Pujita Rama Patra Saraswati Bhagavati Nisheshadadhyapa. Remembering the Almighty and the Goddess Saraswati, I feel that this is such a great auspicious day for me to welcome you all for the great event on the National Conference. First of all, I take the blessings of late Sri Venkatapati, founder chairman of EPGA, and remembering him before I welcome Srimati Ramadevi, chairperson EPGA, Sri Pramod Gowda, CEO EPGA, and Sri Rajiv Gowda, CEO EPGA, in their absence here. I welcome today's chief guest, Dr. C.R. Ramesh, Dean and Innovations, Presidency University, for all his cooperation and for accepting our invitation to be the chief guest and the conference chair. Sir, I welcome you, sir.
Thank you.
I welcome our principal, Dr. S. Prakash. Anything we say is really less about our principal. So enthusiastic and energetic and focused in encouraging everyone in every activity that we carry out here. Sir, we are really delighted to have you here, sir. I welcome for this national conference. Thank you. I request our coordinator, conference coordinator, Anjan Babu, sir, please to hand over a bouquet to our principal. I welcome all the heads of the department of EPCET and other institutions of EPGI. I welcome you all, sir. I welcome all the staff members of the different departments of the EPCET. I welcome you all. I welcome Dr. Ravi Kumar, KP Ravi Kumar, Dean MC Hassan, to be the session chair for the conference for today, and Dr. Shivraj, the professor from RBC. I welcome both of you, sir. I welcome the participants of the paper presenters. I welcome all the staff from all the departments and my own department, Department of Mechanical Engineering. I welcome light and sound provider, Sri Manju Vinod Kemparna. I welcome the media and press on this occasion. I welcome representatives from IJS MME also on this occasion. Thank you all. I would like to brief about the conference. This conference, in fact, we wanted to execute soon after the lockdown is lifted. But we were slightly skeptical on whether to go for offline or online. At this critical stage, actually, when we approached our principal and management, in fact, our principal was so encouraging for us. Nothing will happen. You put all the people back into normalcy. Let's see what will happen. You do online. I'm sorry, the offline itself. We were all geared up to have this offline only, and every preparation and everything was in place. Thank you, sir, for encouraging us to have an offline program of conference. But there was a huge amount of pressure that we subjected to yesterday by the participants. All the paper presenters, they said they started expressing their inability to reach out because of the second wave that is coming up. So we had to budge on that one, and finally we decided, yes, basically this conference is meant for sharing the knowledge, and any conference for that matter is true, that it is for the purpose of sharing the knowledge and knowing to each other and acquiring extra knowledge than what we have already. So based on these lines, and because of this, we finally decided, and also we took the permission of the conference chair and also the program chair, and we decided to go for an online. So thank you very much for all those who have logged in online, and also those who are present here in this seminar hall in the EPCET campus. Thank you all. I welcome once again all of you. To give little extra details about the conference, we had received totally around 58 papers. I'm sorry, 67 papers we had received, out of which 9 papers we have rejected. And out of the 58 numbers, 19 papers have come from professionals, and 20 from the researchers, and 11 from the master's students, and 8 from the UG students. So one paper, in fact, has come from US. Usually what happens is that international papers, international conference, getting a paper from international participants is a very rare occasion. But this national conference has got an international paper. We are associated with IJSME, and we really thankful to them also at this occasion. And all these papers, and I mean to say, the selected papers will be published in that channel. Thanking you, and back to Dinesh.
Thank you, sir. Now, I would like to call Professor Nayana for the invocation song.
Sorry, I request Siva sir to come and occupy the dais. Please, sir. Please come, sir.
If he's scared, we don't know. But if he's, are you scared, sir? Where is he?
I am scared, sir. I am sitting here.
Oh, okay, no problem.
ವಿನಾಯಕ ನಿನ್ನ ಪಾದಕ್ಕೆ ನಮ್ಮ ಪ್ರಥಮ ಪ್ರಣಾಮ. ವಿನಾಯಕ ನಿನ್ನ ಪಾದಕ್ಕೆ ನಮ್ಮ ಪ್ರಥಮ ಪ್ರಣಾಮ. ಲಕ್ಷ್ಮೀ ರಮಣ ಶ್ರೀ ಹರಿ ತಂದೆ ನುಡಿದೆವು ನಿನ್ನಯ ನಾಮ. ಶಾರದೆ ಮಾತೆ ನೀ ಪತಿ ಸಹಿತ ತೋರಿಸು ನಿನ್ನಯ ಪ್ರೇಮ. ಪಾರ್ವತಿ ದೇವಿಯ ಹೃದಯ ವಿಹಾರಿ. ಪಾರ್ವತಿ ದೇವಿಯ ಹೃದಯ ವಿಹಾರಿ ಹರನೇ ಪುರೆ ನಮ್ಮ. ವಿನಾಯಕ ನಿನ್ನ ಪಾದಕ್ಕೆ ನಮ್ಮ ಪ್ರಥಮ ಪ್ರಣಾಮ. ತಂದೆಗೆ ಪ್ರಣವವ ಬೋಧಿಸಿದಂತ ಷಣ್ಮುಖ ಬಂಧನೆ ನಿನಗೆ ಗುರುವೇ ತಂದೆ ಗುರುವೇ ತಾಯಿ ಗುರುವೇ ತಂದೆ ಗುರುವೇ ತಾಯಿ ನಮಿಪೆವು ಗುರುಗಳಿಗೆ ವಿನಾಯಕ ನಿನ್ನ ಪಾದಕ್ಕೆ ನಮ್ಮ ಪ್ರಥಮ ಪ್ರಣಾಮ ವಿನಾಯಕ ನಿನ್ನ ಪಾದಕ್ಕೆ ಶತಕೋಟಿ ಪ್ರಣಾಮ.
Thank you, ma'am. Now, I request the dignitaries on the dais to light the lamp.
You'll have to go there.
Virtually live.
I also request Dr. Ramesh sir to light the lamp virtually.
On behalf of Ramesh sir, we are
On behalf of Ramesh sir,
Thank you. All the best. All the best.
anyone who has submitted the paper to the conference, come up from the in-house.
thank you all.
As it is, audience also. Capture.
Thank you, sir. Now, I would request our ever energetic principal, the program chair of the event, to address the gathering.
Yeah. Yeah, can I start? Yeah.
Sir, I'll address for few minutes, Ramesh sir, and I'll come back to you.
Please go ahead. Please go ahead. Yeah.
Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parat Brahma, Tasmai Shri Guruve Namaha. We did our first international conference, supported by many industries, supported by University of India from Italy, and this is our second conference in the recent times also. Let me first thank our chairperson, Madam Rama Devi, East Point Group of Institutions, Mr. Pramod Gowda, CEO, East Point Group of Institutions, Mr. Rajiv Gowda, CEO, East Point Group of Institutions. They had a very busy schedule today. In fact, Rajiv sir had committed that he's going to come for this conference. For our international conferences, their presence was physically here, but unfortunately, they have packed up with a lot of activities today, and they have sent us a message for the good wishes for this conference. On behalf of the complete organizing team, I thank both the CEOs and the chairperson, Madam, for supporting this conference. Madam, and both the CEOs, thank you so much. Let me thank and congratulate Department of Mechanical Engineering under the leadership of Harishanand uh, for hosting this conference. Let me thank all the advisory committee members, very specifically to my own friend, my boss at my time, Mr. Ramesh sir, research and head of innovations at Presidency University. Sir, thank you so much for taking up our
Thank you.
conference.
Thank you.
Let me thank all the delegates and the research scholars, students, industry professionals for keeping faith in our conference and giving the papers. Very good papers we have got this time. It's amazing to see. Thank you so much. Coming to the conference, I'm not the right person to speak about the conference. Anyway, keynote address will be done by my guru, Mr. Ramesh sir. But what I know from my computer science background is that today, in case IoT has taken a bigger shape, it's because of material science, because of sensor technologies. Now people are all speaking about biopaper sensors, black sensors. Probably in case if IoT makes up a full deployment as per Industry 4.0, it is going to change the complete landscape. Very recently, I was watching the news. The French army is actually going to impose a biochip into the soldiers, where soldiers will be not infected with any of the attacks that comes out from any of the army soldiers. This is something remarkable. Probably biosensors, which come from the material science domain, could be the next biggest revolution that's going to happen. It could be paper-based biosensors, or it could be film-based biosensors, or even it could be chip-based biosensors. So all these things, probably material science would make bigger impact in the healthcare sector. I think we need to reform the healthcare sector, more specifically for India. Many times we need certain technologies which are very, very cost effective for Indian culture and Indian environment. I keep on telling my students and my research scholars, the technology what works for Europe or US may not get fitted into Indian environment. We need technologies which are very, very cost effective for Indian environment, for Indian culture and Indian public. So with these things, I feel material science, technology and mechanical engineering still is a real core engineering. Very unfortunately that, very sad, why the trend is moving towards computer science, I don't know in terms of admissions. Very openly I'm making the statement, being a computer science professor. The core engineering really lies at mechanical engineering, electronics engineering and electrical engineering. I always felt that the real engineering, even at computer science, it happens only at application level. Yes, of course, but bottom layers it do happen. But even either it could be in any sector, either it is aerospace engineering or it could be healthcare sector, even manufacturing a small stunt that goes into my heart for an heart surgery is again a mechanical engineering design and it is in a simple device which also comes from the material science. So mechanical engineering plays a very, very important role in any engineering. So I request and I thank the Department of Mechanical Engineering and all the advisory committee, most specifically to the Ramesh sir and even the Shankar sir who is there with him. Thank you so much for being with us and supporting this conference. Once again, thanking all the organizing committee for making this conference a grand success. All the best. Thank you so much.
Thank you, sir. Now, I would request Dr. C.S. Ramesh, Dean, Research and Innovation, Presidency University, to present the keynote address.
Yeah. Okay, shall I start? Yeah. Yeah. Okay. Yeah, shall I start? Okay. PPT. Very, very good morning. And I'm highly excited and very much delighted, very, very happy to be a part of this conference, especially which is very apt, recent advances in mechanical engineering and materials. At the outset, let me thank Dr. Prakash as well as Dr. Harish for giving me this opportunity to share some of my research experience in both materials as well as mechanical engineering. So what I have for all of you is that today the advancement is at the interdisciplinary. So I would like to just spend some 2-3 minutes on the topics what Prakash sir covered. Because when you are talking about advancement in mechanical engineering, now we are talking about societal impact. 4 areas are very important for us. One is health sector, the impact on power, very important. The third is about the automotive, that is, I'm talking about the transport sector, that is, it can be automotive, it can be aerospace. Now, just to give you an example, and the latest one we are talking about is the drone technology. So, for all of this, unless and until one has got a knowledge about electronics, knowledge about computer science, knowledge about programming, we cannot be having any advancement in mechanical engineering. So that's very, very important. And as he rightly pointed out, we are now in the most advanced stage. What I meant to say here is we need to have communication between two automobiles. So what is that we are talking about? So it is just that a combination of both electronics, mechanical, IoT, and so on. And today, other area is about the agriculture. So we also need to look at what is that we are contributing in terms of research when it comes to mechanical engineering or material science, in terms of having an impact on agriculture. So look at the yield of, say, for example, grape. So you need to really understand, when you look at the technology, you need to really understand when you can actually have the what I should say, taking out the grape at the right time. So what I meant to say here is, when you talk about a grape, you're talking about the wine industries. And now it's very important that you pluck the crop at the right time. And then you need to avoid the diseases. Now look at the leaf of the grapes. So remember, you can get to know from the color of the grape leaf what the disease is. So what I'm trying to do is, I'm trying to build an intelligent system where I can get to know, yes, comparing the standard leaf, looking at the image analysis and the AI techniques, you can just come out and say this is the disease, and then based on that diagnosis you can have the right injection of the pesticide at the right time. So that is where we are looking at the IoT, we are talking about the drones, we are talking about the cameras, we are talking about the image, and then the analysis part. And then in that regard, big data is now coming into picture. And then again, look at the intelligent cars we are talking about today. A lot of things are there. 60% is your electronics. So you're talking about monitoring the vibration. You're talking about monitoring the tire pressure. For all these things, again, you're talking about sensors. Very important. Now, how do you package? So packaging is a key thing there. So that's a challenge. So what we need to understand here is, it is not just you're talking about advances in mechanical engineering. Now, what are the challenges in the frontier technologies? How I address these challenges, and then how I move on. The other challenge for a mechanical engineer or anybody is that the computation. So we would love to have huge amount of computation, but I want the maximum speed of computation. So what is that happening? As a mechanical engineer, I need to understand that when you push both above, now I have a major problem or a major concern, that is heat generation is the key. So what is that I'm talking about? Heat generation here is the interconnect contacts. So you have interconnect contacts, and because of which you have the interconnect contact resistances. Remember, Intel is spending billions of dollars to address this issue, because once you have the heat evolution, as an engineer, as a mechanical engineer, I need to address how to dissipate the heat. So the question here is, all of you have seen, you have the fan, that is a forced convection, and then you are trying to remove the heat. But at the same time, there's also called as a heat sink, and that's where you have an aluminium block. Now, the main purpose of this is that it dissipates the heat. Look at your LEDs, you have the heat sinks. So, what I'm trying to tell you here is, as a mechanical engineer, I need to address the challenges in all these advanced technologies. What I'm trying to tell here is that now people are not just talking about only the high-end computation, but I also need to understand design, use all the tools like CFD and so on to really optimize my heat dissipation. So if you can dissipate the heat, you are the winner. In other words, you are trying to get the maximum performance. So that's where I am now. Today we are talking about high performance computing machines. So you can now understand the amount of heat that is going to be generated, and the challenges that the mechanical engineers do face. So that's one thing. The other one, before I get into my PPT presentation, is my 3D printing, which I'll be addressing. But then look at the technology, which has really been handy for all of us in being innovative. So the first area that comes to my mind is your bio implant. So look at this knee joint. Remember, the structure, the dimension of the joint is specific for a specific patient. And as a mechanical engineer, I'm now contributing here in understanding the load coming on that. What type of loading? Is it a repeated loading? Is it tensile, compression, bending, combination, and then the constraint? So look at the shoulder joint, the constraint is different. Look at the elbow joint, the constraints are different. Look at the knee joint, the constraints are different. So I need to understand a lot of physics behind this, a lot of understanding of these human parts is necessary before you give a solution as a mechanical engineer. And in that regard, 3D printing, has come out as a boon because when you look at the orthodontics, right? So all you do is you get a 3D scanned, you get a scanned picture, and then have a combination of these views, and then combine them, and then you get what I have, the exact tooth structure of that particular patient, and then you don't mind paying 3 lakhs because it's so precise. So as a mechanical engineer, I need to now understand, can I minimize my assembly? Or when I'm talking about the assembly, I need to really understand the dimensions. How precise I am is very, very important. And in this regard, this technology has really revolutionized. Okay, and the other one is the biomedical stent. So you can look at the analysis of this stent. Remember, these are all in sheet form. You just fold it, and then you have it deployed in that particular positions. And that is where today mechanical engineers are involved, really designing. And I think I have covered most of it, and I will just elaborate in detail about three things: the challenges, the challenges, the challenges in 3D printing of metal composites. The other one, the challenges in conventional metal composites, and then I will also talk about the computational fluid dynamics when it comes to the surface engineering. Now, so I just I hope I have touched upon all the relevant topics, which are the themes of this national conference in advances in mechanical engineering and materials. I think whatever I have just said has been or will be an eye opener to all of you, so that you can go back to your institute and start working in these areas of interest and motivate your students to work in these areas. So now I think I'll just go to my slides. So I'll just go to my slide. The first topic is I hope you're able to. I hope all of you are able to. Are you able to see the screen? Hello? Are you able to see the screen? Hello? Hello? Hello?
Yes, sir. Yes, sir. Thank you. Yes, sir.
Okay.
We can, sir. We can.
Hello? Okay. Yeah, you can. Right.
Sir, please go ahead, sir. Thank you.
So, let me just address the challenges. I will not look into the technology because the technology is well proven now. So, as Prakash sir was pointing out, a lot of technologies are coming into picture, especially here. What people are looking at here is you have your design, you have your model. I will just come to that. See, look at this. See, look at this. I will just come to that one particular one. Yeah, just have a look at this now. This is your CAD model, right? What you see to the left is the CAD model of a particular component. And now what is there onto the right is the 3D model, is the one which is already manufactured using the 3D printing process. Remember, it is a metal based printing I'm talking about. Now, please understand that this technology is quite expensive. The reason is two things. Please understand. I'm now talking about a technology wherein I'm making use of the laser power to sinter the particles and then trying to get the components as in the CAD model. Now remember, the investment is huge because of the design of the laser system, and not just that, even the powders are very, very expensive. So the real challenge here is, again, how do you control the dissipation of heat? How do you control the thermal gradient? Now, what is happening here is, as you just notice here, now the laser beam hits the surface of the powder which is spread, and then what you see is a red region. Now it gets sintered, and then I'm trying to move the laser beam across and then trying to get the sintered layer. So it's a layer by layer deposition, and then you get a component as I showed here. This is one component which is called which is nothing but a deflector. What you notice here, which is one of the component for your ball screw assembly. Now the problem was that now when you push the ball against the deflector wears out. So now what we did was we used a hard material, and when you look at a conventional technology of coming out with this deflector, of manufacturing this deflector, is normally they go with a two-piece deflector and then they do the assembly. This is what I told. So 3D printing is one technology which will avoid the assembly of the parts. So whereas in a 3D printing, I can get the functional part. So there is a lot of difference between just a component and a functional part. So therefore, when you look at this technology, as I told, although it is expensive, this is going to be a tool where your creativity plays a very important role. And then not just that, as I told here, this particular component, if you look at it, it will take 3 months to get into this component. Whereas when you do by our 3D printing, it will just take around just within 48 hours, you can get the component done. So, as I have been pointing out, now what people have been doing here is they're exploiting this technology for, as I told, bioimplants. So a lot of work is being done, in really converting, as I told, the MRI, what I call as the MRI scan data, and there is a software which will convert this MRI scan into the CAD model, and from the CAD model you are getting the component. It can be ABS plastic, it can be, as I told, a metallic component, and the beauty of this is that very short time, productivity is pretty high, and not just that, your design, you can have infinite number of design. I mean to say optimization using CAE tool. That is the beauty of this. So you have already optimized and you have got the product straight. So you're not even talking about a prototype, you have the actual component. So what I just want to tell you here, the challenge here. So although this is a sound technology, well-proven technology, but please understand the challenge is this. The challenge here is about the crack. Please observe the cracks, So you have invested huge amount of money. You have the best technology here, but unfortunately, if you don't understand the process, what is that process I'm talking about? It is the heat transfer that is the key which dictates the quality of the product made from this laser sintering. So if you just observe these cracks are because of the huge thermal gradient across the layer, because of which you have huge amount of stressing and you have the thermal stress, and that is where you have the crack. And all of us know that the thermal stress is what? Alpha Young's modulus into delta T, right? Delta T is what I'm talking about, the temperature gradient in all the three, gradient in X, Y, Z, and there you have the cracking. So this is a very, very important thing which as a mechanical engineer we need to understand is how do I monitor this? So how do I, because now you already have the advancement. This is what I'm trying to talk about, the advancement. Today, within the machine, there are already thermal scanners that are available to monitor the temperature of each layer as you keep building it, and then there are then you have a feedback which will ensure that you control the laser motion or the laser power to the level that is desired, so that you are controlling the gradient, the temperature gradient. So what I'm trying to tell you here is not just the temperature gradient, but also there are some softwares and some improvisation wherein which also gives you the elemental composition. So what I'm trying to tell you here is since I'm talking about the solidification, resolidification, and somewhere you also have unmelted portions, and somewhere agglomerations are there. So therefore, this is basically fundamentally we should understand the resolidification kinetics, and if you can understand that, you can predict the microstructure. So unless and until you have a high quality microstructure, you can never dream of achieving a good product in terms of mechanical and structural integrity. So the key is understanding the phenomena, and as I told, heat transfer is the key issue here. And and also we should know which material you are looking at, because look at aluminium. So you cannot be working with aluminium on the laser because the reflectivity is pretty high when you talk. So therefore, I also need to understand the interaction of laser with different materials, and work on that. So just because the technology exists, you should be very much aware of all these fundamentals. Okay, so I think this technology. I think all of you are now clear the challenges what you need to address, because this is the one which is going to now revolutionize your automotive sector, aerospace sector, and even naval sectors, and even day-to-day components, so artifacts. So any of these things, so therefore bio implants, orthodonts. So therefore, I think all of you have now got an idea about the challenges in this technology. So I think having covered this, let me go to the next exciting area. Next exciting area, what I'm talking about is about the computational fluid dynamics. Now, it's a very, very important area, where you need to really understand about the the dynamics of the particles, about the phenomena, and I also need to predict the flow pattern. I'm talking about the fluid. So whether it is a compressible fluid, whether incompressible fluid. So you really need to understand the flow phenomena. And what I am talking about here is adopting computational fluid dynamics to understand a very important technology called as thermal spraying process, which will help you in addressing issues like wear, corrosion in so many areas. Like for example, power sectors. It can be the naval sector. It can be your automotive. So I'm talking about liners. So therefore, what I'm talking about is the technology, especially high velocity oxy-fuel, because when you look at a thermal spraying, it can be, I'm talking about, it can be wire spraying, it can be plasma spraying, and so on. Just to give you an idea about the importance of HVOF, right? Please go back to a very important phenomena, that is wear of your landing gears. I think all of you are familiar with the landing gears. So how are you mitigating the wear there? By using hard chrome plating. So remember, hard chrome plating, it is environmental, definitely it is not environmental friendly. So now everybody is putting a ban through legislation in many of the countries to ban the hard chrome plating. So now, how do you replace that technology? So you don't want to do hard chrome plating, but then what is the next alternative? The next alternative is the high velocity oxy-fuel thermal spraying of hard carbides, and within metals, developing composites, a very hard surface using this technology. So now, what I will do is, before I talk about the computation fluid dynamics to optimize the process parameters, I will just try to just make you just have a look at this. So it is basically, if you observe this process, you have the most important element here, that is your gun, and this is the nozzle, and the design of the nozzle is very, very important, because the kinetics of the flame is very important. What is the heat content of the flame? How do I control the flame temperature? And now, what do you mean by optimization? Now, what is the optimal distance between the gun and the substrate? So very important. So you need to optimize the distance between the gun and the substrate, and also now what is the temperature, as I told here. So what is it? What is the temperature profile of the particles that are coming out of this gun, and at what temperatures and at what velocity the particles will go and hit the substrate? That is very, very important. Now, what you are observing here is, is repairing of some sort of a roller that are used in textile mills, whatever it is, right? So that is where it is being fixed to a shaft. Now, what I'm trying to tell you here is, this technology is very much advanced. And when I went to Sweden, that is University of West, they are trying to work on this technology for so many applications. And along with this, they're also looking at what is called as, they're also looking at the plasma technologies, but this technology is what widely being used, and for various industrial applications. Just to give you one more example is, all of you have seen the boring, right? So when you go for your what I should say, deep ground boring, now you have got one pipe, other one, so it's basically cascading one. So it is subjected to a lot of slurry and so on, and it gets corroded and so on. So so you cannot be taking any chance. So that is where they are trying to come out with solutions using this technology and trying to make it as hard as possible and as corrosion resistant as possible. So now, because CFD happens to be one of the conference theme, I'm trying to just make all of you understand the importance of this computational fluid dynamics tool in solving problems related to thermal spraying, right? So, having just told, let me just try to make you understand now how it works. Basically, now there are three things we should understand here. Now, this is your nozzle, and now I'm talking about the fuel oxygen. This is very important because this ratio, what I call as a stoichiometric ratio, that is the one which is going to help us in generating the heat that is necessary to melt the powders. Very important. So therefore, so optimizing this proportion of fuel oxygen is very important. And then is the compressed one, because I want the powders, powder, I'm talking about a carrier gas. Normally they use nitrogen now because I do not want any oxidation of the powders to happen. So once, so there are different techniques. Don't worry about it, whether it is gas fuel or kerosene fuel. Don't worry about it. What I'm talking about is the velocity. Look at the velocities, pretty high, very high, close to around 600 meters per second. And because of this high velocity, the bond between the substrate and the coating is very good. And the deposition efficiency is excellent, I'm talking about. And then, now I just want to just make you understand here that look at this now. So I'm talking about a gun which is commercially available. So this commercially available gun, okay, what I had was the HUOF setup that was supplied by a company called Metallizing Equipment from Jodhpur, and the details of the gun is what I'm trying to demonstrate here. We did the model, so we maintained the dimensions of that gun, and for our gun we have done the optimization study. So look at this, the gun, and then you have most important aspect here. How do I inject the powder? Where do I inject the powder? These are called as injection points. So this again is very important because at the end of the day, how you inject the powder is very important, and because the quality of the coating depends upon how much of powder you inject. So that optimization is very, very important. And so this is just the dimensions. And I will just come to all this meshing and so on. All I just want to just make you understand here is the predictions. Now just look at these predictions, what I'm talking about. I'm talking about the particle size. Look at the particle size. Now, the powder, it can be 20 micron, 40 micron, 60 micron. You know very well I'm talking about the powder that are commercially available. It can be 10 micron. Now, the question here is, what is the optimal particle size? And then for a given particle size, what is the injection velocity I should look at, right? So what will happen? So remember, when you look at this pattern, there is going to be wear and tear of my inner surface of the nozzle. So I need to ensure that most of the particles are within this range, so that the interaction of my hard ceramic particles onto the inner liner is minimal. So what happens? My wear out of the inner surface of the nozzle is reduced. Similarly, always understand that my particle velocity is very, very important. Higher the velocity, please understand, the quality of the deposit is very good. If you just notice, if the injection velocity is something around 10 meters per second, I'm getting a very high velocity as the distance also increases. So the standoff distance is again very important, and you can just the particle temperature. Look at the particle temperature. The particle temperature is maximum when the injection velocity is at 10 meter per second. So what I'm trying to tell you here is, if I'm injecting at 10 meter per second for a 20 micron particle size, my temperature is maximum. My particle temperature is maximum. That means the temperature of the particle coming out of the nozzle, that is very important, and that is maximum. And then you can look at the distances too, and you can optimize. And remember, with these optimized conditions, we were able to solve an industrial problem. That is, what we did was, we did coating of inconel and titanium powders um, on a worn out, I repeat, on a worn out plunger. So that plunger failed because of a lot of corrosion, as well as wear and so on. And in fact, there was also fracture. So what we did was, we took that company name is Gayatri Bio Fuels. So then we took that this one failed one. We did the analysis, and then we did the coating, and then we put it back, the plunger. And in fact, I'm very happy to inform all of you that this has got a patent. So we were able to solve an industry problem. So the industry problem was solved looking by optimizing the process parameters using computational fluid dynamics. So now you can understand, we need to really have a domain knowledge, and then integrate this domain knowledge to solve an industry problem. That's what I was trying to demonstrate here. Then I will just go to the next one, about the development of lightweight materials today for engineering applications. The world is moving towards experimenting this. Look at I don't know how many of you have heard of this Renault, right? Look at many of the automotive companies. So they are trying to replace aluminium alloys with aluminium composites. But again, as I told, challenge. Lot of challenges there. How do you really get a quality metal matrix composites for a specific application? I'm very happy to share with you that my lab, we were able to develop a composite material for what I call as a piston for SG. That means for application in defense. So let me not elaborate more on that because it's highly confidential. The testing was done, and we were able to clear the testing rounds. And so what I'm trying to tell you is, we need to address the challenge to develop a quality MMC. So I think I have some time, I think, right? I have got how many more minutes? Hello? Yeah. So let me just share with you my experience with metal matrix composites, because this is also one of the I gave a presentation at Wipro too, if you notice, at their Wipro infrastructure engineering, because we were discussing on the 3D printing of MMCs. Look at the challenges here. So the challenges here is in the secondary processing of MMCs. And then about the choice of matrix and reinforcement. We are all engineers. We just know that composite means it is just playing with two materials. No, it is not. you need to now address three things. One very important thing is, what is the thermal mismatch? Very important. What is the thermal mismatch between aluminium and silicon carbide? What is the thermal mismatch between aluminium and titanium carbide? What is the thermal mismatch between aluminium and carbon fibers? What will be the chemical reaction between aluminium and carbon fiber? Can you prepare aluminium carbon fibers just like that? Can you do that? So what are the challenges? Because if you can do that, you are the winner. Because for any applications, it can be space, it can be aerospace, it can be automobile. Fundamentally, I'm looking at three things: specific weight, specific modulus. I repeat, specific weight, specific modulus. So when look at aluminium, combination of aluminium and carbon fiber, nothing can beat their combination. You get the maximum specific strength, maximum specific modulus, and low, I'm talking about low specific weight, very high, I'm talking about the specific weight. So look at the density of aluminium, look at the density of carbon fiber, very low. So therefore, but on the other hand, what is the challenge? Lot of reaction exists between aluminium and carbon fiber because of their chemical affinity. Aluminium will react with carbon fiber and form aluminium carbide. One possibility. And then wettability. Carbon fiber do not wet molten aluminium. So what is the way? So the only way is addressing these challenges. Look at this. I'll just come to the I'll just come to the yeah. If you just look at this now, I'll just come to sorry. Just look at this photograph. Just look at this photograph. Beautiful distribution of silicon carbide in aluminum matrix. And now you can comment on this as having a uniform distribution, and not just uniform distribution. There is an excellent bond between the matrix and the reinforcement. Now remember how it was possible? As I told here, when I'm looking at the processing, I'm processing through a primary processing using liquid metallurgy route. Again, I use a CFD to optimize the rotational speed and then the depth to which the blades need to be immersed. I get a uniform distribution, and not just that. Please look at this nickel coated silicon carbide. Why do I coat a nickel phosphorus electrolytes on silicon carbide? The main idea is addressing the challenge of avoiding the reaction between aluminium alloy and silicon carbide. Because aluminium will react with silicon carbide and form aluminium carbide. Aluminium carbide is highly brittle. We are all mechanical engineers. Please understand that you are developing a quality composite, but unfortunately, the material will not be will not function to the desired design. I mean to say, it fails because there is an inherent brittleness because of the presence of aluminum carbide. So the challenge here is minimizing the reaction between aluminum alloy and silicon carbide. And if you can do that, this is where you get a quality composite material. And I'm very happy to inform you that some of the publications what we did got the attention of Renault. So they wanted to ensure that we develop composites for automotive applications. So therefore, so the applications like, if you just, I'll just go back to the look at this now. This is the floating piston, what we developed for, as I told, for defense applications. And how is it done? So you have a casting, remember? So we used a casting simulation tool. We used Procast. We looked at, because initially the casting is 325 mm. Now, how do you ensure that it is a defect free? Now, once you have the casting, it goes to the extrusion. Now, from 320, I have to reduce it to, remember, 110 mm. And then it is followed by forging. So now you have got casting, followed by extrusion, followed by forging. Now, remember, forging and extrusion of composite is highly challenging. I'll just show you the problem here. Look at this now. Look at this press now. What happens here is, my lubricant is very, very important here. So we had a lot of challenges. When you have the extrusion being done, remember this for a small size. For my piston, it's a huge one. I was using the silicon carbide heaters. Then the graphite lubricant was a challenge. So we had to use molybdenum disulfide. So selecting the right lubricant, and then selecting the right extrusion ratio, and then the temperature, the billet temperature, all these were optimized again using the deform software. So analysis is the key thing. Prediction is the key thing. Unless and until you do the analysis right, your manufacturing fails. So what I'm trying to tell you here is, casting, we did the simulation, then we designed the die, the molds, and then from there we put it on to the extrusion. Then we did the extrusion under optimized conditions, and then we were able to get good components, and then we were able to do the forging. So what I'm trying to tell you here is look at this now, extrusions. So only problem here, when you look at the extrusion, what I'm trying to tell you here is the distribution is along the direction. I repeat, it is along the direction of your, I should say, along the direction of the extrusion. So you know very well that when you do the extrusion, the properties, you know very well, are definitely not isotropic, right? So this is one information, and you should also be aware of, because the properties will not be uniform, right? Then just a difference. When it is uncoated, see the distribution, and when it is uncoated particles, see the distribution, and you can now understand what are the challenges, how to address the challenges, and so on. Also, just to give you an idea, the understanding, look at this uncoated one. You see the formation of aluminum carbide. So what is that I'm talking about is the last one, characterization, material characterization. Now, how to know whether the reaction has been reduced or not? Now, just look at the second figure. There is no formation of aluminum carbide, whereas in the first case, aluminum carbide reaction, because of the reaction between aluminum and silicon carbide, you have the reaction and you have the intermetallic phase, and it fails. So therefore, this is one characterization. So as mechanical engineer, we also need to understand what is characterization. So you need to look at characterization for microstructure, characterization to understand whether any intermetallic phases are formed, whether there is any phase transformation from, as I told, from a ductile phase to a brittle phase. So these characterizations are very, very important to really come out finally with a high quality manufactured product or a component. That's very important. And the other thing which I just want to share with you is about the tribological applications today. Everybody is talking about reducing friction, wear, and so on. And in this regard, there are so many developments that are happening. For example, people are looking at graphene, because everybody is now looking at the nanostructured material, to really improve the mechanical properties as well as reduce the friction. So look at graphene. Graphene is one potential candidate for developing a composite material because number one, the thermal conductivity is pretty high. So wherever you're looking at heat dissipation, your objective is heat dissipation, you can always look at that because when you look at silicon carbide, it's a ceramic material, right? So therefore, you need to, as a mechanical engineer, you need to design the material for a specific application. So I think I have done my address. How to have interactions with all the participants. So I really love to have questions from each of you. Please go ahead, and I would like to know from the organizer whether if there is sufficient, if there is some more time, I can continue with further insight into the advances in mechanical engineering. Yeah, please. Yes, Prakash.
As usual, sir, it's a great technical stuff. Fully packed, sir. Amazing to see you back. Thank you, sir. Sir, what do you see? What could be the next future? I think you were specifying about implanting and all these things.
Correct.
And if the large-scale deployment of sensors happens, either it could be health, and if the convergence of all sector converges at one point, what could be the future of material science, sir? What do you predict?
Yeah. See, there are two things here. As you pointed out in your inaugural address, biochip, you are talking about a chip, lab on chip, whatever you call. So what basically it does is you have a you are talking about MEMS and NEMS. I'm talking about, so what happens there is sample of the blood is sucked and then pumped, and then it does the analysis, and then these parameters, for example, viscosity. The viscosity has got something to do with your temperature, right? So therefore, and the blood pressure, all these parameters, what I call as a vital parameters, they're all monitored, and then you're talking about this data being transferred to the doctor from the patient. So that is where the technology need to come. So what is the speed at which it is being done, and it should not be any disruptive. So the data should not get disrupted, right? That's very important. So that's where there are some issues there. Look at the robotic surgery now again, right? So somebody gives the command there, and the surgery is happening at somewhere, right? The doctor is in Chennai, and maybe somebody is doing the operation, right? But then what I'm trying to tell you here is understanding each of these is very important, like understanding the operation, and then what is the procedure. Unless as a mechanical engineer, if I do not understand that, I will not be able to really employ the technology, right? That's number one. Number two is about the communication, right? So somebody should be there to really evolve the technology of transferring the data in real time. So your response time is very important. So there are two things. One is the sensor, one is the actuator. So both are very important here. And how you embed the sensor? What is the what is the technology of coming out with those sensors? Because again, it's a question of biosensors. And then not just that, what are the parameters that you are looking for, right? So that's very, very important. And most important is the packaging. So this is a very, very important challenge. So people are facing. Yes, sir.
Thank you, sir. Thank you.
See, because what happens is when you transmit high quality pictures, and when you at the other end when you start opening it up, it takes a lot of time, right? So that is right now challenge.
Correct, sir.
Yeah. Any questions, please, from the audience?
1 second, sir. Any questions from the audience? Someone? Any questions from the audience here?
Only two things. If they don't ask me question, that means I have not done my job properly. Or Prakash, I have not done my job properly, or the other way around, right?
Correct, sir. True, true. Sir? Shiva, sir? Have you a question? No, come, sir. Please come and ask a question, sir. Yeah, sir is asking. Sir, 1 second.
Yeah, please, sir. I will be here. No problem. Till I answer all the questions.
The problem is with the technology. Many times we are with a new norm of virtual environment here. So some interruptions will be there, sir. Getting the people here. 1 second. I think I have Professor Shiva here. He's a mechanical professor. He has a question, sir. 1 second, sir.
Yeah.
Good morning, Ramesh sir.
Yeah.
This is Shiva.
Yeah. Please.
We met many places virtually, physically, and all things. And now we were all enjoying the bits and pieces of technology you were delivering. And the question is, have you ever mentioned about that the countries are going away from completing? Is there any reason? Is there any hard chrome plating? Countries are shying away. Are they?
Artist. No, you tell me. Can you come again, please? I'm not able to hear.
During
Yeah. Now
you mentioned, I heard you making a mention of the hard chrome plating. Countries are shying away and they are going for some, ultra modern plating method. So, what is the reason for this shift?
hard problem. Can you type your question? Can you type the question?
I think there is an interruption.
Yeah, you can type the question. I think that is the best thing.
I'll post it personally and get the answer. Thank
Yeah,
you.
please.
Thank you. Thank you.
Yeah, there is one question here. How CFD?
Sir Ramesh sir, we have a question from one of the audience which is visible on the screen. Mr. Nutan Kumar is asking how CFD is used in material science and welding.
Yeah. Shall I take this? Okay. Yeah. It's a very good question. Just now I showed you in my second talk how CFD is used in optimizing process parameters for thermal spraying, right? When you look at a thermal spraying, you have already, you should understand that you will be wasting a lot of experimental trials, lot of time in experimenting things. What should be the distance between the gun and the substrate and so on, and so powder. What should be the powder size, and what should be the fuel air ratio, so on. All these things you can optimize using the computational fluid dynamics. Is what I in fact I showed you this slide, right? So in fact I can if you want I can leave the PPT with you. So that's one area. Welding. See what I'm talking about here. Welding is that. See here basically you cannot be looking at welding. What you can do here is how you cool. So that's very important. So cooling, today people are moving towards use of nano fluids and so on, because that will have a lot of effect on the microstructural aspects of the weldment. So I think definitely you can look at the CFD very effectively in these areas. And as I told, it's a generic one, what you are talking about, material science. So CFD is definitely great tool, for any of the simulation. When I am talking about phenomena like heat transfer and so on, right? Please, yeah. Yeah, and not just that, you are talking about complex geometry shapes for aerofoils and so on. It's very, very important to see. Yeah. Yeah. Next. Yeah. Any other questions?
Good morning, Dr. Ramesh.
Yeah. Good morning, sir.
Hello, sir. Do you hear me?
You will be wasting
Good morning, sir. My name is
trials. Lot of time in
my name is Dr. A.K. Shukla.
What should be the distance between the gun and the substrate and so on, and so powder. What should be the powder size, and
Sir Ramesh sir, we have another question from one of the senior professor here. Over to you.
Sir, good morning. My name is Dr. A.K. Shukla.
Oh, good, sir. Good. Nice to meet you. Yeah.
And I have one curiosity question.
Please, sir.
You mentioned about 3D printing of materials.
Correct.
And I just wanted to know whether this 3D technique has been used on semiconductors, for deposition of semiconductors, particularly for energy conversion device like thermoelectrics.
Correct. Sir, now what has happened is, for example, see, it comes in different, there are so many techniques available. Okay. For example, fuse deposition and so many techniques where you can have a low melting material like ABS plastics and so many things. And in fact, there are so many articles available where people have used for the circuits also.
Okay.
Right? It's already been done. It's already there. A lot of articles are there, and only thing is you can definitely control what I should say the miniaturization is the key thing here, right? And only thing here is your resolution is important. So whether I'm building a 5 micron, 2 micron, 1 micron, 25 micron, so there are machines where we should have a capability of very good resolution. That's very important. I cannot be building some 25 micron with from a machine which is having 25 micron. I cannot be getting to 5 micron. So if I can build 1 micron, 5 micron level, my surface finish is going to be excellent, right? So likewise, so what I'm trying to tell you here is it depends on the capability of the machine. That's very important. So it's there already. A lot of literature are available.
Yeah.
And yeah, because you are a chemistry professor, I also want to tell you the advancement in the 3D printing is the development of new materials.
Yes,
So
sir.
if you
I'm talking about thermosensing materials.
perfect.
Because this is
So
very
if you,
new area. It is technology for the future. Lot of
Sure.
heat is getting wasted. We can convert into electricity using thermosensing materials.
so
And
yeah,
it can be deposit thin layer using 3D
correct.
technology.
Correct. So therefore, if you can just get some thermal properties of that, like for
Yeah.
example, what is the melting? What is the melting point of that? What is the thermal capacity of that, and all. And depending on that, I can suggest you can we do it or not, because we have got some 1 or 2 machines with us. Okay, one very low cost machine we have got. The other one is at PES, right? It's a very good one. And other one we are trying to procure where we can use powders, nylon powders. So from nylon, I will just show you. Just 1 second. Just 1 second. Yeah, can you see this? Yeah, can you see this? Can you see
Yeah.
this? See
Yeah,
this.
we can see this, but not very small object. Yeah.
Yeah, see here.
Yes, sir.
Now?
Yeah. Yeah, now it is clear. Now
Now,
it's magnified. Yes, sir.
this is a nylon one. So this now you can see, right? So this is
Yeah.
this is a nylon one, and
Yeah.
you can see one small ball also inside here.
I understand.
So
Yes, yes,
what
yes.
I tell you is, so this is highly
It is
sophisticated
3D
one,
printed
a
article.
3D
Yeah,
printed one.
yeah.
So people are looking for professors like you who can develop novel material. We'll discuss later, sir. I think it's a
Yes,
good
sir.
idea.
No, I mean to say this technology can be used for semiconductors for the
Correct.
for the energy conversion device.
Yeah, it depends on the
Like solar
yeah,
cells, photovoltaic cells, or thermoelectrics, things like
perfect.
that.
But only thing is we need to design our own our own
Yes,
deposition
yes,
technique.
yes,
Right,
sir.
that's it.
Right. Thank you very much for all suggestions. Thank you.
Thank you, sir. Thank you so much for your time. Sir, we have another question from Mr. Nutan Kumar.
Please. I'll have more questions.
Yeah. Yes, sir. Question is on the screen, sir.
Yeah. Enlighten us with some facts about generative design. I would like to know from him what exactly he means by generative design, because I'm not familiar with this word. Yeah.
Mr. Nutan Kumar, requesting you to elaborate your question as.
What do you mean by regenerating?
Okay. Okay. Meanwhile, when we get the comment from the panelist or the people who are here, we have another person to ask the question. Over to you,
Please.
sir.
Sir, good afternoon, sir. Sir, this is Sadia from East Point College. Sir, now 3D printing is at middle stage.
Correct.
Now people are talking about the 4D printing on fluids. So how it is derived from 3D printing, sir? Can you?
This again, I think it's very new to me. I am not that. I am not. I have no idea about that. Right? Let me admit that. I have no idea about that.
Sir, I have another question. Sir, say in the structural components, even though we have so much of composites, there are few elements where, say, the alloys which can't be replaced. So, what are the shortcomings of these newer materials that has been addressed by the alloys?
See, these are all parallel developments. See, you cannot say that you will not be using alloys. You will go to the only advanced materials. No, because see what happens. This is what I told. You have to be very specific for a specific application. Because when you look at the standard alloys, right, that holds good for a general. But when you're looking at a specialized product, right, which again will have a lot of components. So each component can be specially designed. So then you pay more extra. You have to pay extra money, right? Because the material is innovative, the design is innovative, right? So that's the way. So you cannot say that, okay, now we have come to the advanced stage, I'm going to discard the earlier alloys. No, they are already well proven, right? So we need them well industrially accepted, process is all standardized, right? So that is, yeah, please. Yeah.
Thank you, sir.
Yeah.
So thank you so much for your patience and the explanation, sir. Mr. Nutan Kumar has come with a question, sir.
Yeah.
You have
Yeah.
asked.
Topology
He is
optimization.
listening.
Yeah.
Yeah.
This is a very interesting one. When I'm talking about the surfaces. So now surfaces are very important when I'm talking about the surfaces of for example of the automobile. You look at it, right? So so look at the look at the automobile, right? So when you look at the exteriors, right, these surfaces are what I'm talking about, the most critical aspects, right, or aerofoil, right. So any of these are very critical for me, right. Now, when I'm talking about development of a composite material now how do I arrange the fibers? So in a polymeric material, so I need to now maintain the geometric complexity, but at the same time, I also need to develop good bond between each layer and also have a control over the fiber and the matrix bonding. So this is very important because if the interfacial bond fails, then the component fails. So therefore, this is a very challenging one, and that is what you are talking about, the material optimization in terms of the laminated composites. So that is what I think you are talking about. Definitely the material optimization when you talk about the laminated composite is very important. How the fiber is oriented, whether I have got a zero ply, 45-degree ply, 90-degree ply, very important. So you may have a combination of 0, 45, 90. So therefore, you know very well that the mechanical properties of each of these fiber, 0, 0, 45, 90, entirely differs. And so the combination is very important, and that is your design, right? Yeah, I think I have cleared your doubt. Yeah, please.
Thank you so much, sir, for your kind words and the explanation. I'm sure Mr. Nutan will be delighted to have his question solved. We can see the response. Yeah, he's writing thank you, and his question is solved. Thank you so much, Ramesh, sir, for your patience and time, sir. With this, we have a lot of questions which are floating in YouTube. What I will do, sir, if as the time does not permit us for further question
Okay,
answer session,
good.
we will pose the questions directly to you. You can answer them. We will send the answers back to the audience.
Yeah,
With
good.
this, come to the
Good
conclusion.
interaction. Good, yeah,
Thank
good
you so much.
interaction. Yeah, thank you very much for all the arrangements. I think we didn't had any problem, no technical hitch. So thank you. You have done a wonderful job, right? Thank you.
Thank you, sir. Thank you so much, sir. With this, we are ending our question answer session. And over to Professor Dinesh for vote of thanks.
It's my pleasure to give the vote of thanks. And I would like to thank the management of East Point Group of Institution for giving us this facility and the infrastructure for having this conference. Also, I would like to thank the chief guest and the conference chair, Dr. C.S. Ramesh, sir, for his valuable time in enlightening us with this useful information and very rare information nowadays. You know, because these information are very critical. Thank you, sir. Also, I would like to thank the principal and the program chair, Dr. Prakash, sir, for his encouragement in carrying out this event. I would also like to thank all the HODs of all the departments for their support. I would also like to thank the sessions chair for their patience and for their support for the event. Also, I would like to thank the advisory committee and the organizing committee for making all the arrangements and the support for the event. I would also like to thank the staff of the department for their effort for staying late and preparing or arranging all the facilities. I would like to thank the staffs of the department, the participants for their effort in preparing and sending us the paper and believing in us. Thank you for the participants, media representatives, sponsors. I thank you all, and everyone who directly and indirectly supported us. I would offer my sincere thanks from the Department of Mechanical Engineering. Thank you all.
Sir, thank you, sir. Ramesh, sir, thank you so much.
I hope it was. I hope it was good, and there are some contribution.
Absolutely, sir. I think we loved your session as usual. Thank you
Good.
once again, sir. We'll keep on disturbing you for more sessions next time, sir.
No problem. Thank you.
Thank you, sir.
Anand.
Thank you so much.
Yeah,
Thank you, sir.
Thank you.
Bye.
The paper presentation will start in Google.
I know it's here.
Sir, to all the participants, the paper presentation will start in 15 minutes time, and it will be in the Google link. Please check your mail for the Google Meet link. Thank you.
Thank you, sir.